We will
Good afternoon,
today.
sir.
Good afternoon. Good afternoon. So today I will discuss about thesis, linear independence, and rank nullity theorem, row space, column space. Before that, last time I stopped at complete solution, how to find a complete solution of a system. So I'll discuss about a little bit, then I will go to the further discussion. Okay. So the first question, and if you have any, since only you present one person, so if you have any queries from the previous discussion or in the current discussion, you can ask anytime. Okay, you can stop me and ask me anything. The first example is we need to find the complete solution x. So x is basically what is complete solution, that is a particular solution plus null space solution that we have discussed before. Okay. Uh, of the following system. What is the system? System is it's a 1 2 4 2 4 8 1 4 6 0 8 8. So there are x1, x2, x3, x4, and we have 4 to 10. So, so the first thing what we have to do, we have to basically augment A and B matrix, and then we will get 8, and then if I do augment, that is 4 to 10. Okay, and then we have to do the Gauss elimination method. So what we can do, we just change the R2, that is R2 minus 2R1, and R3 is R3 minus 4R1. So what we'll get is 1 2 1 0 4, that is 0 0, this is 2 2, this is 0, so this is 8, and this is 2 2 minus 8 is minus 6, right? And here 0 0, and here 4, this is 2, this is 8, this is 16 minus 6. Okay, so next thing that we have to do is, sorry, R3 is, so R3 is R3 minus R2, and what we'll get 1 0 0 2 0 0 1 2 0 0 8 0, and then 4 minus 6 0. So since we have a 0 equals to 0 format, that means there is a solution exist. So the first thing that we have to do is particular solution. So how to find out the particular solution? We said that in the previous week, we have said that when we find out the particular solution, what we have said. So in case of particular solution, we choose a free variable to 0, and we choose the pivot variable. So here, what are the free variables? So in that case, what are the free? This is the pivot variable for first row, pivot variable for second row. So similarly, these two, that is x2 and x4, are free variables, right? That means non-pivotal variables. So here we have to choose x2 and x4 0. So my particular solution is x3, which is equals to, if I put x, if I put x4 to 0, what would be what would be x2? X3, it would be minus 3. X4 to 0, this would be minus 3, right? So this is 0, this is minus 3, this is 0, and this would be minus 3, this is 7, plus 7. So this is one of the particular solution. Now we have to find out the null space solution. Null space solution means we have to find out the solution of Ax equals to 0. So we have to find the x for which this Ax equals to 0 equation can be satisfied, right? So in that case, in that null space solution, what is the ultimate so in null space solution, we do not need this b, because in that case b is equals to 0, right? We have to find out the solution where this kind of scenario exists. This kind of scenario exists. Okay. So since we have a two free variables that we have said, that I have said before, x2 and x4. So what are the choices? First, we have to choose x2 equals to 1 and x4 equals to 0. This is the first choice. And the second choice is x2 equals to 0 and x4 equals to 1. This is the second choice. So we'll get two solutions, right? So S1, the first solution of null space S1, when x2 1, x4 0. So if x4 0, what would be x3? x3 should be 0, right? From this equation, we can say that if x4 equals to 0, then x3 equals to 0. Now x3 equals to 0, x2 equals to 0. Sorry, x2 equals to 1 over here. So what would be x1? x1 equals to minus 2, right? So this is the second solution, a first solution of null space, and the second solution. Second solution, what is second solution? We have to choose x2 0 and x4 1. So if x4 1, what would be x3? x3 should be minus 4, right? x2 0, so minus 4. So here x3 is minus 4, and this is plus 4. Okay, you all get it? So therefore, my complete solution x equals to, that is xp, sorry. So what is null space solution? That is xn equals to the alpha 1 s1 plus alpha 2 s2. So all the all the null space that are spanned by these two vectors, all the null space that are spanned by these two vectors, the s1, this s1 and s2 are basically, uh, you have to find out the linear combination of these two vectors, which are the solution of, which is basically the solution of null space. Okay, now x equals to basically xp plus xn. So what is xp? So xp is basically minus 70, and it's sorry, plus 70 minus 30 plus alpha 1 minus 2100 plus alpha 2 40 minus 41. So what is alpha 1 or alpha 2? Alpha 1 and alpha 2 are belongs to some real number. So any real number, you put any real number over here from any negative zero, positive, any real number you put over here, and you do this addition, do this addition, you will get the solution. So that means, so as we have already mentioned before that, since the here the system has maximum, system is basically, if you see this, so this is basically 3 cross 4, right? The system is 3 cross 4. So maximum rank that we can achieve, that is basically a fat matrix. Okay, that means the variables are more than the number of equations. So basically maximum rank that a matrix can achieve is 3. Okay, so we have seen already in previous uh, class that in case of fat matrix we will always get a infinitely many solution, whether it's a, I mean, whether the matrix is full rank or matrix is a not full rank, whatever the scenario, we will always get infinitely many solution until and unless 0 equals to, if something happens in the last equation, if after doing the Gauss elimination process, if we do not get this 0 equals to 0 form, then we will get no solution. So if 0 equals to 0 form, we achieve this 0 equals to 0 form, then whatever the rank of the matrix is a full row rank or matrix is not full row rank, in both cases we will get infinitely many solution if the a matrix is a fat matrix. So here we get less than, with the rank is basically 2, the less than which is less than the row rank. So obviously we get, and this 0 equals to 0 solution, 0 equals to 0 format achieved. So obviously we get infinitely many solution because there are infinitely many real numbers over there. So put any real number, you will get a solution over here. Okay. So this is basically, from here uh, we can say the rank of a matrix. So we have already discussed this in in maybe in first class or second class, whatever. The rank of a matrix. So what is the rank of a matrix? We know that number of linearly independent columns or number of linearly independent rows are basically mention the rank of the matrix. So here are basically, if you see there are two, linearly independent columns. Why they are two linearly independent? Because the pivot elements lies in these two columns. That's why these two columns are linearly independent. So that's why the matrix is, the rank of this matrix is 2. Or you can say we have two linearly independent rows. Okay, because we cannot this 0 0 0 rows is basically always dependent rows. We cannot consider it because no pivot element over here. So there are two independent rows, and or you can say two independent columns. So that's why the rank of the matrix is 2. So from here we can I just okay. So from here we come to the concept of rank nullity theorem. So what is rank nullity theorem? So the rank nullity theorem says that dimension of system, whatever the system that we have considered, is basically dimension of null space plus rank of matrix A, or rank of matrix A is basically, so here we can say rank of matrix A is basically dimension of column space. So this is basically a calligraphic C. The dimension of column space is basically rank of A. So instead that we can write it over here, dimension of column space of A, right? So here Just a minute. Yeah. So, here, so in the given system, what is the rank of A? Rank of A is basically 2. Okay. So what is the rank of A and what is the rank of uh, null space? So so we will discuss this rank nullity theorem after we discuss about the basis and how basis is related with the dimension. So let's just this portion skip for the time being. I'll do one more example from this complete solution, and then I will move to that basis. Okay. So, another example. Another example, it says that we have a system something like that. It's a 1, 2, 2, 3, 2, 4, 5, 9, 3, 6, 7, 12, and we have x1, x2, x3. This is equals to b1, b2, b3, and b4. The question is, what condition on b1, b2, b3, and b4 make the system solvable. So we have to find out the condition on b1, b2, b3, b4 so that the system is solvable. Okay. So first of all, normal, we have to find that A augment B, and we will see that so this is basically, this is right now is a tall matrix. It's not a fat matrix because number of equation is more than number of variables, right? So this is basically a tall matrix right now. So we will get a unique solution or zero solution. Let me check. Yeah, we will get a zero solution or one solution. So there is no possibilities of getting infinitely many solution. So we have to find out the R2 is R2 minus 2 R1, R3 is R3 minus 2 R1, and R4 is R4 minus 3 R1. Okay. So 1, 2, 3, B1, this is 0, 0, 0, B2 minus 2B1, this is 0, this is 1, and this is 1. This is b3 minus 2b1, and then this is 0, this is 1, and this one is 3. I think this one is 6, right? This one is 3. So here b4 minus 3b1. So here we have to do row exchange. Before row exchange, I just want to do another row operation, then I'll do the row exchange of yeah. So here basically I need to change, let's say R3 is basically R2 minus, sorry, R3 minus 3 R2. Okay, so this is 0, 0, 0, b2 minus 2b1, then sorry, here R4. So this is R4, R3. Okay, 1, 1. This is B3 minus 2B1, and here 0, 0, 0. So what we get? B4, okay, B4 minus 3B1, that is multiplied with 3 R3, so 3B3, 3B3 plus 6B1, right? I hope I did the right thing. Please check this calculation, last one, if anything wrong over here or not. So what is basically the solution? So the solution is 1, 2, 2, 0, 0, 0, B2 minus 2B1, 0, 1, 1. It's a B3 minus 2B1, and the last one is 0, 0, 0. So it is become B4 B4 minus 3, sorry, plus 3B1 minus 3B3. So now we have to make it an echelon form. So we have to exchange the row. So let's say R2 is exchanged with R3, and what I will get 1, 2, 3 B1, then 0, 1, 1, B3 minus 2 B1, then 0, 0, 0, here 0, 0, 0, and here we'll get B2 minus 2 B1, and another 0, 0, 0, we'll get B4 plus 3B1 minus 3B3. So from here, what are the conditions? So this term should be 0 because we need a solution. So for this case, this should satisfy 0 equals to 0 format, and this should also satisfy 0 equals to 0 format. So this term should be 0 and this term should be equals to 0. So these are basically the condition that P2 should be equals to 2B1 and B4 plus 3B1 minus 3B3, that should be equals to 0. So these are basically the condition to make the system solvable. Okay. So now So in that case, if we say that we have to find out the solution of this matrix, solution of this system, so what will be the particular solution? You need to find out the particular solution of this system. What will be the particular solution? So so here is one variable is free. So which one is free variable? The free variable is here, the pivot one here. X1 is associated with pivot column. X2 is associated with pivot column. So that means X3 is my free variable. So put X3. So what would be the choice? So choose X3 equals to 0. So the particular solution XP should be something 0. And what will be if this term is 0? This should be, what will be the X1? X1 should be 2B1 minus B3, right? Sorry, B3 minus 2B1, B3 minus 2B1. So if X1 is B3 minus 2B1, put that value X1 plus 2 into B3 minus 2B1. This should be equals to B1 because X3 is 0 over here. So what will be the X1? So X1 would be B1 plus 4B1 minus 2B3, right? So it is 5B1 minus 2B3. So this is my particular solution. Okay. This one is my particular solution. Now, next move to the concept of linearly span, independence, basis, and dimension. Okay. So when we talk about independent vector means the number of vectors that we are basically concerned about, whether these vectors are independent or dependent. So the number of vectors are basically, there are no extra vectors. Like if say in in R2 plane, R2 plane means in XY plane. Okay. So XY plane, in XY plane, the number of independent vectors you can consider as a, let's say 0, 1, 0 and V2, 0, 1. So if we consider these two vectors, are they independent or dependent? So definitely, I mean, there is a process to find out whether the vectors are independent or dependent. But by intuition, I mean, by seeing these two vectors, we can see that these two vectors are independent. Independent means we cannot produce V1 only using, we cannot produce V1 only using V2. Because when I'm talking about V2, so there is a Y element exists. So Y element exists over there, but there is no X element. In case of V1, there is a X element exists, but there is no Y element. So that means we cannot produce V2 by only using V1, or we cannot produce V1 only using V2. But if we consider another vector V3, 1, 1. So is V3 linearly independent with V1 and V2? If I say, if I ask that V3 is linearly independent with V1 and V2, so definitely the answer will be no. V3 is not linearly independent with V1 and V2. Means we can express V3 by just adding V1 plus V2. By just doing this operation, we can express V3. But if I ask, is V2 linearly independent with V3? Forget about this V1. Forget about this V1. Okay, I'm just asking that if is V2 linearly independent with V3? So in that case, yeah, definitely V2 is linearly independent with V3. Because why? Because V2 only consists Y element. There is no X element, but V3 consists X and Y element. So we cannot solely produce V3 only using V2. Similarly, we cannot solely produce V2 only using V3. This you can see by seeing this kind. I mean, it is possible, but when move to this higher dimension like 4, 5, yeah, 6 dimension vectors, so it is quite difficult to understand these things just by seeing, right? So that yes, definitely V2 and V3 are linearly independent. Similarly, V1 and V3 are linearly independent, but V1, V2, and V3, these three vectors are not linearly. These three vectors are not linearly independent, right? Understand the concept? So if you picture it, so this is, let's say this is one vector, that is V1. Okay, this is V1, and let's say this one is V2. So using this vector addition format, this is V3, right? So V3, V2 are linearly independent. V3, V1 are linearly independent, but V1, V2, V3, these three are not linearly independent. So from here, the concept of spanning comes into the picture. First of all, what is spanning? When I say, are these vector can this vector span the space, span the R2 space or not? Can these vectors span the this R2 space or not? Definitely, right? I mean, we can find any vector, we can design any vector, because we are talking about only xy plane, right? I mean, when I'm talking about xy plane, that means you have to consider the negative x, you have to consider the negative x as well as negative y. Okay, so in this xy plane, we can design any vector by using the linear combination of these three. So we can design any vector v by using a linear combination of these three. But is this vector really necessary to span the space? Can anyone answer this? I mean, this v3 vector is really necessary to span the space?
No,
Okay,
sir.
no. Yeah, so answer is no, because we have v1 and v2, and by using these two vectors, we can span the whole space. This v3 is not necessary. That means this vector is extra. This vector is extra. That means this is not necessary. Similarly, if we talk about v1, if we not choosing the v1, let's say, so v2 and v3 are sufficient to span the space. We do not need v1. Similarly, v1 and v3 are sufficient to span the space. We do not need v2. Okay, so that means to span the space, only to span the R2 space, only two linearly independent vectors are required, not three. That means the third one is basically the extra. So here comes the concept of basis. So only correct number of vectors are required to span the space, span the particular space. So those set of linearly independent vectors are called bases. So here you can, and basis, always remember, basis is not unique. Okay, so here the first basis you can consider as v1 and v2. This is basically the most common basis for R2 space, right? So you can consider basis as V1 and V3. You can consider basis as V2 and V3. Okay. As long as the vectors are linearly independent and they can span the space, those vectors can consider as a basis. So in the set of basis vectors, so this is basically you can consider as a basically set of vectors who are basically linearly independent and span the space. So in the set of this basis vector, the number of vectors basically defines the dimension of the system. Okay. So now comes the dimension of the system. So what is the dimension of the system? So dimension basically number of vectors exist in basis. So is this clear to you all? What is basis? What is linearly independent? What is spanning the space? And what is the dimension? I hope I'm able to clear this concept. So in this case, since if you see every unique whatever the bases are not unique, but the dimension is both cases are unique, right? It has to be. That means in B1 we choose a different independent vector, but there are only two vectors up there. In B2 there are only two vectors. In B3 only there are only two linearly independent vectors. That means the dimension of the system is 2. So here comes the now here I come to the rank nullity theorem. So dimension of the system is dimension of null space and dimension of column space. So when we talk about dimension of column space, so for the particular system, I don't know whether I can take a copy this. So this was the basically the picture. So here we say that the rank of A is basically dimension of column space. So dimension of column space means these two are the linearly independent columns. Okay, because pivot element exists in these two columns. So the basis of column space of A basically 1 0 0 and 1 2 0. So as you can see, there are three elements in each vector, but the last vector is 0. That means you can consider like it is basically in 3 dimension. It is basically in 3 dimension. Okay, but z element is always 0. So that means all the vectors lies in this xy plane, right? All the vectors lie basically in this xy plane, in this whole xy plane. That means whole xy plane can be spanned by this. Whole xy plane is basically considered as a column space of A, and it can be spanned by these two vectors. So the basis of column space is basically, what is the basis of column space? This is the basis of column space. Number of vector exist in basis of column space are 2. So dimension of column space 2, which is basically the rank of the matrix. Now, if you see what is the rank of null space, dimension of null space. So if you see from here, The dimension of null space is basically, you can see there are two free variables are there. So that means you can get a two solution. So these two are the, sorry, these two are the bases. Okay. These two are the basis for null space of A. Okay. So that means basis for null space of A right? So you can see that null space belongs to Rn. Sorry, I mean R4, whereas column space belongs to R3. That means the number of variables, basically the number of variables basically defines the number of elements in each vector of null space. So here the number of, so the basis of null space is these two vector are linearly independent, that we get. How we can say these are linearly independent? Because we choose one free variable, one of the free variable as 1 and 0 for one case, and second case as 0 and 1. So definitely these two are the linearly independent. And so the dimension of null space of A is basically 2. Now, what rank nullity theorem says? It says the dimension of system is equal to dimension of null space of A plus dimension of column space of A, right? So that means 2 plus 2. So here basically 4. The dimension of the system is how many variables are there. That basically decides the dimension of the system. So when we talk about the dimension of system, that means total how many variables are there, how many variables we are basically dealing with to solve this set of equation. Sorry, to solve this set of equation. So that means dimension of system is basically dimension of null space and dimension plus dimension of column space. So here basically the rank nullity theorem uh, satisfied. So I hope up to that point everything is clear to all of you, right? Now move to that. Okay. So move to that linear independence. So what is, every time I said that the two vectors are linearly independent. So what is basically the linear independence mean? Basically, what is the meaning of linear independence? So when we say that V1, V2, Vn, this sequence of vectors are linearly independent. This means that the combination, let's say alpha 1 V1 plus alpha 2 V2 plus up to alpha n Vn, this combination will always give 0 if and only if alpha 1 equals to alpha 2 equals to alpha n, they all are 0. That means we cannot find any non-zero coefficient over here to make this addition to 0. Make this addition to leads to a 0 vector. If we cannot find any non-zero coefficient to make this combination, make this addition leads to a 0 vector, that means all those vectors are linearly independent. If we find at least one combination to find the to make this to lead this addition to lead this addition to 0 vector, so that means all these vectors are not linearly independent, they are linearly dependent. We have to remove that vector 1 or 2 vector from that set of vectors to make the system, to make that set linearly independent. Okay. Just like if I give you the example of linearly independent and linearly dependent. The first one, vectors 1 0 0 1. These two are linearly independent, definitely. The second, if I choose v1 equals to, let's say, again 1 0, and v2 let's say 1 comma 0.00001. So is this vector are v1 and v2 linearly independent or dependent in that case? Can anyone care to answer this question? In this question number 2, I said that v1 is 1 0 and v2 is 1 comma 0.00001. Since I'm just talking about only R2 space, so you can say this by seeing these two vectors. I mean, there is no need to go for calculation. So if you want to go for calculation, you just put these vectors into a column of a matrix. Put those vectors into the column of a matrix. So 1 0, you have to put 1 0 over here, and then 1 and 0.0001, and then find out the determinant or do the Gauss elimination method. Check the number of pivot elements, and then you can find out the rank of the matrix. If the rank of the matrix is 2, that is full rank, then these two vectors are linearly independent. If it is not full rank, that means these are not linearly independent. These are linearly dependent. Now, please tell me, are these two vectors linearly independent or not? V1 and V2 over here.
Linearly independent, sir.
Yeah, these two are linearly independent because how small that value is doesn't care, but this is always greater than 0. Okay. In this case, this is always greater than 0. How small this? So definitely this term is non-zero term. Linearly independent. Now if we say v1 equals to say 1 1 and v2 equals to -1 -1. Are these two vectors linearly independent or linearly dependent in this question number 3?
No, they are linearly dependent.
Yeah, they are linearly dependent because v2 is minus v1. That means linearly dependent. That means alpha 1 v1 plus alpha 2 v2 equals to 0 when alpha 1 equals to 1 and alpha 2 equals to -1. So that means here you have to make this addition 0, you have to have alpha 1 and alpha 2 both should be 0. But here the case is alpha 1 equals to 1 and alpha we get a non-zero coefficient, so that means they are linearly dependent. The last one, are these vector linearly independent or dependent?
Independent, sir.
No, they are not linearly independent, they are linearly dependent because of this zero vector. Now you'll say how it is possible. So if I say alpha 1 v1 plus alpha 2 v2 equals to 0, right? So I have to put 0 into v1, but I can put any non-zero value. Alpha 2 could be any non-zero or zero value, right? Let's say minus 1 multiplied with v2. Still I will get 0. Because minus 1 is multiplied with 0 vector. So still I will get 0 vector. So alpha can be any non-zero, any zero value. We don't know. So because of the existence of the zero vector, the system, these two are linearly dependent, not independent. Clear? So now the next question is, in R2 plane, can any three vectors, let's say whatever, let's say v1 is AB, v2 is, let's say, CD, and v3 is EF, be independent. The question is, any R2 plane, if we choose any three vectors. So can we say that all these three vectors are independent with each other? Is it possible? Yeah, I'm just asking a question. So is it possible that in R2 plane, R2 plane means only X and Y axis, there is no Z axis. Okay. So in R2 plane, if we choose any three vector from this R2 plane, we choose any three vector from this R2 plane, and we say that these three vectors are linearly independent with each other. So is my statement correct or wrong?
So they are the linearly dependent because B1, B2, 3, 3 are in number, and this is the R2 plane. So
Yeah.
one more vector is there.
Yes. So that means when we're talking about R2 plane, so maximum number of vectors can be independent with each other are number 2. Okay. Because this is the number of the, this is basically the basis. Okay. This is basically, as we have discussed before. So this is basically the basis. So number of vector existed in basis are basically the dimension of the system. So dimension of the system I have said is R2, and here number of a basis should be two vector should be existed in basis. More than two vector can't be possible, and basis means the exact number of vectors, those are linearly independent and span the whole space, right? So definitely, if we're talking about R2 plane, so the answer is, if we're talking about R2 plane, three vectors can't be linearly independent. Okay, so one vector, there has to be existed a one vector which is the combination of the other two vectors. Okay. So similarly, a few questions we will discuss about. Okay. So show that V1, V2, V3 are independent, but V1, V2, V3 and V4 are dependent. What are the V1, V2, V3, V4? So V1 is 100, V2 is 110, V3 is 111, and V4 is 234. So first we have to consider three vectors V1, V2 and V3, and we have to check that these three vectors are linearly independent or not. And then we have to check that if we add another vector with those three vectors, then the whole set V1, V2, V3, V4 are linearly independent or not. So the first process is you can put all those vectors. Let's say I'm considering a matrix A where the columns are V1, V2 and V3. Okay. Now put all those vectors in the column. So it is 1, 0, 0, 1, 1, 0 and 1, 1, 1. So this matrix is basically already in echelon form. You can do it in row echelon form as well. So if you do it in already in row echelon form, you can do it in a reduced row echelon form. So if you do this reduced row echelon form, you will get an identity matrix. Okay, simply you will get an identity matrix. So because in reduced row echelon form, you have to make the element above pivot element should be 0. So you have to make these three terms to 0. If you make these three terms to 0, so reduced row echelon form would become identity matrix. So from here, you can consider that what are the equation? You have to find out when I'm talking about linearly independent, and in case of this, so that means the null. So that means you have to you have to check that this Ax equals to 0. The solution, there is no non-zero solution. There does not exist any non-zero solution. The solution that exists in null space of A is x equals to 0, 0, 0. Only 0, 0, 0 vector exists in null space. Okay. Other than that, there is a no non-zero x you will find. So if it is possible, that means these are linearly independent. Let's check whether this is possible or not. So from here, the first equation is x1 plus x2 plus x3 equals to 0, then x2 plus x3 equals to 0, and then x3 equals to 0, right? So these are the three equations that we get from here. So put x3 over here, you will get x2 equals to 0, and then put x2 and x3 over here, you will get x1 equals to 0. So the solution is basically x equals to x1, x2, x3, and these are 0, 0, 0. Okay. So that means only 0, 0 solution exists in the null space of A, and A is created with putting all the vectors that we are basically concerned about in a column of matrix. So that means V1, V2, V3 are linearly independent. Now similarly, we have to check whether if we add V4 over here, so is it whole this V4 along with V1, V2, V3 are linearly independent or not? So let's say consider a new matrix A tilde, sorry, A tilde. The first one is V1, second one is V2, third one is V3, and fourth one is V4. So you can see this is a fat matrix. That means number of variables is sorry, number of variables is more than the number of equations. Okay, so there are 4 variables but 3 equations right now. So if we add V4 to this, so that means this is 3 cross 4 matrix. So maximum rank that can achieve is basically 3. More than 3 is not possible. So definitely from here you can see that the number of variables is 4 and number of rank can be achieved is 3. Maximum rank can be achieved is 3. So definitely the matrix is, I mean, we will never get a 0, 0, 0 vector. We'll never get only 0, 0, 0 vector in null space. We'll get some non-zero vector as well because of this x4 element, right? Still, we will do the Gauss elimination process to check whether how is it possible. Is it required? I don't know. I don't think it's required. No, I don't know. I don't think it's required because these are already these are in echelon form. Yeah. So what are the equations? X1 plus x2 plus x3 plus 2x4 equals to 0. Then x2 plus x3 plus 3x4 equals to 0. And x3 plus 4x4 equals to 0. So now you can see there are 2 pivot elements. Sorry, 3 pivot elements. 1, 2, 3. And there is a 1 free variable, right? That is x4. 1 free variable. Right. So when we have 1 free variable, we cannot choose 0 because there is only exist 1. So if we choose x4 as 0, so all values that we get basically 0, 0, 0, 0. So we cannot choose 0 for that case. So in that case, choose x4 equals to any non-zero value. So it's better to choose 1. You can choose any non-zero value. Instead of 1, you can choose 2, -1, whatever. But it's better to choose 1 because it is easy to calculate. And the span, and this is basically the basis vector of the null space. So you can say that this whole span can be whole space can be spanned by this space. Okay. So if we choose x4 1, what would be x3? So x3 would be -4. Put x3 and x4 over here. So what we will get, x2 equals to -x3 minus 3x4. So you will get 4 minus 3. So that means 1. And x1 equals to -x2 minus x3 minus 2x4. So what we'll get is -1 plus 4 minus 2. So that is equals to 1. Sorry. So what is the solution? It's 1, 1, -4, 1. So we get a non-zero solution, right? That means x equals to 0 in this system. In this system, basically we did not get any zero solution. That means there exists if we talk about this alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4. Now if we choose alpha 1 is 1, so 1 multiplied with, I'm not writing over 1 over here, so 1 0 0 plus 1 1 0 minus 4 4 4, because I'm multiplying with -4, and v3 is 1 1 1 plus 2 3 4. So what we get is 1 plus 1 minus 4 plus 2, 0 plus 1 minus 4 plus 3, and 0 plus 0 minus 4 plus 4. So what we get is 0, 0, 0, right? So that means there exists non-zero alpha i's for which we get this solution, this combination to 0. That means these four vectors are not linearly independent. They are linearly dependent vectors. Okay. So that's why in R3 plane, similarly, similar to the previous case, where the question was in R2 plane. So here in R3 plane, four vectors can't be linearly independent. The maximum linearly independent vectors can be three vectors in R3 plane. So that means only V1, V2, V3 are here basically linearly independent. But if we add V4 to this system, so we'll get a linearly dependent solution. I hope this is clear to everyone, linearly independent and linearly dependent. Is it clear to everyone?
Yes, sir.
Yeah. So there's a last question, something, I mean, it's a so the question is, suppose V1 up to Vn is a basis of Rn, and the n by n matrix, I'm considering that matrix is A, is invertible. So it's sort of a proof kind of thing. So show that AV1, AVN is also a basis for Rn. So as I said that basis of particular space is not unique one. You cannot say that this is the unique basis. No, it is not possible because there are lots of vectors, spreading around that space. So you cannot say the bases are unique, but the number of vector existed in the basis is unique. Okay, so that has to be same for every basis cases. So this question says that, okay, I'm saying a V1 to Vn is a basis of Rn. So V1 to Vn of basis is a basis of Rn means there's a n-dimensional system. Okay, and number of basis vector existed is n. So that's why V1 to Vn. Okay. Now it says that if I multiplied this, if I say there exists a matrix A which is invertible, which is not a, whose determinant is basically non-zero. Okay. So if we multiplied that matrix A with each vector and say this is a basis, this is a new basis for that particular space. Is it possible? I mean, is that statement correct or not? That is basically the question says. So definitely the statement is definitely correct because when it says that V1 to Vn is a basis for Rn space, right? So what we can say about this? So using the basis, we can span the whole space. Okay. So if you see the lecture video by Professor Aikerana, so there he had shown one thing, that for a particular vector, if we have to represent a particular vector by of a space by the basis vector, that representation is unique, right? If you see that proof has been already shown in that lecture video. Like, let's say I'm considering another vector is v in that Rn space, and I want to represent that v vector using this basis vector v1 to vn. So if I say that v is basically, let's say, some c1 v1 plus some c2 v2 up to some cn vn, so that representation has to be unique. You can't get multiple number of representation using the same basis vector. If you choose another basis vector, you can get another representation, but using the same basis vector, you will always get an unique representation. That means that C1, C2, Cn values will be always unique if we choose V1, V2, V3, Vn. Okay. So, so that means if we say this V is any vector in that Rn space, and which can be represented by its basis vector, and that is the representation of this basis vector. Okay. So now we have to show the linear independence of AV1 to AVN. How we can show this? Using that formula that we have said over here. Using this formula, you have to show that all the coefficient is 0 leads to the, if all the coefficient is 0, then this addition leads to the 0 vector. Then we can say this V1 to Vn are linearly independent. Okay. So let's say, we can say, suppose C1 into AV1 plus C2 into AV2 plus Cn into AVn equals to 0. Okay. So from linear independency of V1 to Vn, we can say, since C1 is a constant term, so we can multiply it matrix, we can multiply it, we can pre-multiply matrix, we can post-multiply the matrix, so it doesn't matter. Okay. So this C1 V1, so we take common A from here, and the C1 V1 plus C2 V2 plus up to Cn Vn, this is equal to 0. So which leads that, because I have already said that this combination is equals to V, so that means AV equals to 0. Okay. So AV equals to 0 means, and here also I have said that A is non-invert, A is invertible. That means A inverse exists, right? So A is invertible means, implies that A inverse exists. Okay. So that means if we pre-multiplied by A inverse on both sides, so what we'll get? A inverse A V equals to A inverse 0. So we'll get V equals to 0. Right? So V equals to 0 means C1 V1 plus C2 V2 plus Cn Vn equals to 0. Because Here I have chosen that v equals to this thing. So that means this term is equals to 0. So already the statement that is given to us is, since v1 to vn is a basis of Rn, and so not and, so therefore they are linearly independent. That means they are linearly independent. That means C1 equals to C2 equals to Cn 0, which means that A V1 A V2 A Vn are also linearly independent and span the space, which combinedly says that AV1 to AVN, they are this is basically the basis. Okay, is it clear to everyone? Okay. There is a one question. Question says I have a matrix A, something like that, 1 1 1 1 2 3 3 3 6 9 1 3 minus 4 1 minus 2 minus 1 minus 7 minus 7 minus 3 4 minus 3 minus 8. So for that case you have to find the basis of null space of A. So that means you have to find out the solution first. I mean, you have to find out the solution of the null space. That is the main thing. Once you find out the solution, you will find out the basis as well. So the first thing is 1 1 2 3 3 3 6 9 1 3 minus 4 1 minus 2 minus 1 minus 7 minus 7 minus 3 minus 4 minus 3 minus 8. So R2 is basically R2 minus R1. R3 is basically R3 minus 2R1. And R4 is basically R4 minus 3R1. So what will get 1 3 1 minus 2 minus 3 0 0 2 1 minus 1 0 0 2 is minus 2 and it's 4 minus 3 and it's 6 3. Just check the calculation whether am I doing something right or not. Okay, just check it. Just cross check it basically. 0 in here multiplied by 3, we will get minus 2 Model 3 will get -6, -1, -9, 1. It's multiplied with 2, -4, right? -4, -2. -4 -2 is -6. Now, what we have to do is R3 is basically R3 minus 3 R2, R3 plus 3 R2, and R4 equals to R4 plus R2. So 1, 3, 1 minus 2 minus 3, 0, 0, 2, 1 minus 1, 0, 0, 0, 0, 0, 0, 0. So there are two pivots, right? So you can see here is two pivots, that is x1 and x3, and there are three free variables, x2, x4, and x5. So three free variables. So from here we can assume that obviously there exist three linearly independent basis vector for null space, right? Because we have to choose 1, 0, 0, then 0, 1, 0, then 0, 0, 1, right? These are the three combination, primary combination that we can consider. So the first solution is, so if we choose 1, 0, 0, that means x2 is 1, x4 and x5 are 0. So if we choose that, x4 and x5 are 0. From second equation, we can see that x4 and x5 are 0. So that means this x4, x5 0, that means x3 has to be 0. Okay, so x3 is 0. Now here x4, x5, x4, x3 all are 0. This is equals to 1, x2 equals to 1, and this, so x1 should be, what should be, so that we will get this whole thing equals to 0. So x1 should be -3, right? Now S2, now look, if we choose instead of 1, 0, 0, if we choose 2, 0, 0, so you just need to multiply this vector with 2, you will get -6, 2, 0, 0, 0. Okay. Similarly, why I said 2, 0, 0, you will get to see that thing. Next thing is x2 0, x4 1, x5 0. Now since x5 0, so here x5 0, x4 1. So what would be x3? x3 should be -0.5, right? x3 should be -0.5. So if it is -0.5, that means this one become 1 by -1. So -1 plus 1, this will get 0. So now x4, x5 0, x4 1, x3 is -0.5. This is 0, and this is what should be the value. So if you check, go and check, the value should be 2.5. So now it looks like something in fraction. So it's better we will get a whole number. So it will be easier. Just multiply with 2, you will get. So if you multiply this with 2, you have to multiply this with 2 as well to make all the bases in the same cases. So this is 5, 0, -1, 2, 0. And if S3 equals to, this is x2 equals to 0, x4 equals to 0, x5 equals to 1. Similarly, here you will get this term equals to right now is this term 1 and this term 0. So x3 is 0.5, and if you go and check that x1 should be, x1 is 2.5 as well. So this is the span, basically this vector span the space, these two vector, I mean these two vectors span the same space. Similarly, these two vectors span the same space. So whether you choose this one or this one, they span the same space. These two vectors span the same space. Similarly, these two vectors span the same space. So basis of null space, I'm just considering the 100 term only, is 2.50 minus 0.510 and 2.50 0.501. So that means number of basis vector is 3. Number of vector in basis is basically 3. So dimension of null space of A is 3. So dimension of null space of A is 3. How many variables are there? So dimension of system we know is dimension of null space plus dimension of column space. So dimension of, now if we find out the dimension of column space, is basically dimension of system of equation plus dimension of null space, right? So what is dimension of system? How many variables are there? The number of variables is 5. Sorry, this should be minus. Number of variables is 5. Dimension of 3 is 3. So that means column space is 2. So dimension of column space is equals to rank of matrix A, which is 2. Now if you see, you can see there are only two pivot variable existed. There exist only two pivot variable. That means two linearly independent vectors are there. These two. That means the rank of the matrix is 2. So that means rank nullity theorem satisfied. Okay. Now I just touch the last topic. I mean, it's not very case. I mean, not hard one. So row space. So what is row space? So if we say that, if we talk about the column space, the column space means column space of A is basically the space that is spanned by the columns of matrix A. Okay. So similarly, row space is basically, this is the space that is spanned by the rows of the matrix A. Okay. Now, so rows of the matrix A is basically what? If we say rows of the matrix A, so A is A, B, C, D, E, F, I, J, K. So when we say column space of A, column space of A is basically number of, here I A, B as alpha, beta, gamma. It will be better. So the column space means the spaces that is spanned by the columns, and it belongs to, here you can see it is basically 3 cross 4 matrix, right? So column space belongs to R3. Why R3? Because these are spanned by this column, and the number of elements existed in the columns are 3 elements. The column space is spanned by R3. Similarly, if we say row space basically spanned by the rows. Okay, spanned by these rows. Okay, so number of elements existed in rows are R4. So row space belongs to R4. Now you can consider row space as a column space of A transpose. Now, if we do the transpose, what we will get? We'll get A, B, C, alpha, D, E, F, beta, and I, J, K, gamma, right? So now here you can see it has become now 4 cross 3 matrix. So that means column space of A transpose, which is belongs to R4, and row space of A transpose, which is belongs to R3. So that means column space of A is basically row space of A transpose, and row space of A is basically column space of A transpose. So this is basically the concept, and the numerical is very easy. I mean, whatever the numerical that I have shown to you till now, you can find out the row space column space easily. So up to that point, is there any kind of query that I can clear, or is it clear to everyone?
Yes, sir.
Is it clear to everyone, right? So, so you do not have any question then, I hope. So I can then stop this discussion over here.
The last previous two example.
Yes. Yes, last previous two example. This one.
Our previous, sir.
Previous class.
Next, this example.
This example. Okay. This example. Yeah.
Yes, sir.
Yes.
Sir,
Yeah.
last को अपन जो how to use the AV1, AV2 up to AVN are also li and span the space. They line. This line is
Because
not.
I have, because here I have considered this thing, right? I have assuming that this addition is 0. Okay. Now I have to show that if this addition is 0, then C1 to Cn, all this should be 0. Is it clear to you? I'm assuming that
Yes, sir.
if, because linearly, what linearly independent says. So first of all, the first thing that in our statement in question is basically says that V1 to Vn is a basis of Rn. When they say that this is the basis of Rn, that means any linear combination that leads to 0 is it is possible when all the coefficient that is used for the linear combination is 0, right? So I'm considering, since basis can span the space, right? Basis can span the space. So I'm considering any vector, any v vector can be represented by this linear combination. Any v vector. I don't know whether it is a 0 vector or any other vector. Any v vector can be spanned. Now I just multiplied. I said that okay, let's multiply this v1 with a, v2 with a, and vn with a, and I'm saying, so this is my assumption, and I want to prove this assumption is true. Okay, so I assume that the C1 AV1, since A, so therefore AV1 is also vector, because if we multiply multiply a vector with a matrix, so we'll get another vector, right? So AV1 is a vector, AV2 is a vector, AVN is a vector. So I choose that there are another vector, let's say V tilde. Okay, V tilde, sorry, V prime. So instead of saying this, I'm saying, okay, C1 V1 prime plus C2 V2 prime plus Cn Vm prime is equals to 0. Okay. So what is V1 prime? V1 prime is AV1, V2 prime is AV2, and this way. So if this is equals to 0, I have to make that these all are linearly independent. That means C1, C2, Cn all are 0. I have to show that. Okay. So definitely, since this is C1 is a scalar term, C1, C2 all are scalar term. So we can, I mean, we can pre-multiply, post-multiply, doesn't matter. So I just take a common A matrix from here and choose this one. This one equals to 0. So that means this one I have previously said it is a V. So since it is V, so AV equals to 0. Sorry. So if since here basically A inverse exists, because I have already said that A is a invertible matrix. Okay. So A inverse exists, that means what we get V equals to 0. So we get V equals to 0. So that means this equation leads to this, right? This equation leads to this. So according to the linear independence definition, C1, C2, Cn, this all has to be 0 because V1 to Vn are the bases, and basis means they are linearly independent and they span the space. So that means C1 to Cn all are 0, right? So here since C1 to Cn all are 0, that means if we put over here, that means or over here, that means C1 to Cn are all are 0, that means V1 prime to Vn prime all are linearly independent. Is it understandable up to that point?
Yes, sir.
So since V1 prime, V2 prime, Vn prime all are linearly independent, okay, there are n number of vectors, linearly independent, exact number of vectors. That means they can span the whole space. That means they are the basis. Okay.
Yes, sir.
Okay. So I think if there is any
Sir, in the
question,
last example,
in the last example, here,
where you are taking the value of S1, S2, and S3. So we are considering like just you have suppose for example x2 is equal to 1, x2, x3 equal to 0. So we can take any values in place of x2, x4, and x5 for finding S1, S2, S3.
For finding out x1 or x3, you can choose any value of x2, x4, x5. So just choose one value non-zero and other two value 0. It's not necessary that non-zero value has to be always 1. It could be -1, it could be +1, it could be -2, +2, whatever. But just to make sure that you choose one value at a time, one value non-zero, other two values 0, so that the vectors that we get are linearly independent. They are not similar. We do not get any dependencies in nature, because after all we have to find out the basis of null space. Here the question is we have to find out the basis of null space. So the linearly dependencies basically lose the basis properties, right? So to make sure that all the three vectors that we get are linearly independent, for that case we have to choose one vector as a non-zero value, one free variable as a non-zero, and other two free variable as a 0, so that the vector that we get are basically linearly independent. So that's why this procedure basically follows. That's why we say that these all three vectors can span the space. Okay, so that is the main thing. So I hope none of you have any kind of queries. So I just stop this meeting over here. Okay. See you in the next meeting, next discussion. Okay, bye. Thank you.
Thank you, sir.
Yeah.
Thank you, sir.